In this video, we're going to discuss how phasors are going to be worked in with resistors, inductors, and capacitors. For a resistor, that's the easiest result because V of t is just R times I of t, that's Ohm's law. So what that means is if you turn your voltage and current into phasors, you just have phasor voltage is R times phasor current. And since R is just a constant real number here, that means on my graph here that whatever phase angle that your voltage is going to have, your current will have the same phase angle. Because again, you're taking current, multiplying it by a real number. A real number is the same as having a 0-degree phase. And so that means that it's not going to add or subtract any phase from it. In terms of looking at the graphs of the cosines, if one of these is your voltage, the other one's your current, as you can see, they are what's called in phase because the same point where one of them has maximum, the other one also has maximum, same with minimum and so on. So in the case of resistors, they are in phase. There's no difference between the phases of voltage and current, and that's how the phasor is going to work there. On case of inductors, remember that our functions, either V of t or I of t, are just going to be some constant cosine omega t plus phi. And when we turn those into phasors, we have this A angle phi. But what's really going on here, there's really this kind of hidden e to the j omega t there. And when you take the derivative of something involving e to the j omega t, you're going to multiply by j omega there. So the end result over here is when we convert the equation for inductors, it says voltage is L di dt. You're going to have phasor voltage is L. And then instead of just phasor current, so you're taking derivative, it's going to be j omega times phasor current. So what that means is if you take your current, you're then multiplying by this number j omega L. And j omega L, since again omega is a real number, L is a real number, and j is at a 90-degree angle, right? This is the real axis, this is j here. It's at 90 degrees. So this is going to be omega L is your magnitude and your angle is 90. So what's going to end up happening is your voltage is always going to have a 90-degree larger phase angle than whatever your current is. Voltage is going to have a 90-degree larger than your current because you're taking current, multiplying something with 90 degrees means you add 90 to get the phase angle for voltage. So what's going to happen here is that the graphs are no longer going to be in sync. The voltage is going to reach its maximum before its current reaches maximum, and the voltage is going to reach its minimum before the current reaches its minimum. So what we say here is we say the voltage leads the current. Another way of saying that same thing is that the current lags the voltage. So that's what's happening here in an inductor. The voltage angle is always going to be 90 degrees further than the current angle, which means the voltage is going to reach maximums and minimums before the current, which means the voltage is leading the current. One way to remember that is for an inductor, the current cannot change instantaneously. So what's going to happen is the voltage changes first, and then that causes the current to change. That's why the voltage leads the current. Now you're going to have the exact opposite result for a capacitor. So I rewrote, so normally we write for capacitors that I is C dV dt. I rewrote it to look a little bit more like Ohm's law where I put the V on the left side and then something times I. Well, when you turn things into phasor, derivatives become multiplying by j omega. So j omega phasor V equals 1 over C phasor I. And if you solve for this, you're going to get 1 over j omega C. And you can either leave it as a fraction or think of this as negative j over omega c. It might be easier that way. And if you have the imaginary number negative j over omega c, that means your magnitude is 1 over omega c. And because it's negative j, it's in the negative y direction. That's an angle of negative 90. So what's going to happen here is before, when we added 90, the voltage was 90 degrees ahead of the current. Now the current is going to be 90 degrees ahead of the voltage. So here's our voltage. Our current is ahead of that. So what that means in the picture is, again, the current is going to now reach a maximum before the voltage. And similarly, the current is going to reach a minimum before the voltage does. So it's the exact opposite of an inductor here. So instead of voltage leading the current, now voltage is going to lag the current, which is the same thing as saying is that current leads the voltage. So this is how phasors are going to interact with our three most common circuit elements. And it's important to understand how in some cases you're going to have voltage and current in sync. In some cases you're going to have one ahead of the other. For pure inductors, the voltage is ahead by 90 degrees. For pure capacitors, the current is ahead by 90 degrees. And when you start combining, say, RLC circuit, then one or the other may be ahead, and it may be, instead of by 90 degrees, maybe only 20 degrees or something else. So when you have a combination circuit, you can do analysis similar to this to see how far either the voltage or current is leading the other one. But at least for the basic elements, it's either 90 degrees ahead or 90 degrees behind.